Kuzu Zambala. What we are just playing is an indigenous sport of Bhutan called Kuru. It is quite similar to a game of darts. This here is a Kuru.
The game of Kuru has been played by the people of Bhutan for over 100 years, but it became more popular in the early part of the 20th century during the reign of our second king, Dugyalpo Jigme Wangchu.
Today we are going to learn an important concept in physics through Kuru, projectile motion.
In this episode, we will discuss about the developments in the science of projectiles over time. We will then take you on a journey to learn more about the first Bhutanese satellite that was launched on June 29, 2018 called the Bhutan 1. And finally, we will learn more about the different forces that influence the motion of a projectile.
Now, let's delve into how humans learned about projectiles. Humans have observed nature at work and have drawn inspiration to create inventions that have helped in civilization.
Now let's imagine the eruption of a volcano. All of that energy getting accumulated and having nowhere to go until suddenly that awesome amount of energy is then released in the form of kinetic energy all at once. Lava, rocks, boulders are projected at great distances. Perhaps as early Homo sapiens appeared as a species with their highly developed brain and their opposable thumb, they thought, how can I make such a thing myself?
We can only speculate about how our ancestors got inspired to adapt to the natural phenomenon of the projectile in their daily lives. But today, we depend on projectiles more than we think. Do you know the greatest advancements and breakthroughs have mostly happened during times of war? Wars have always needed constant and quick developments. Humans tend to replicate the power of nature for many good things, but often when we see ourselves in danger,
just like throwing a spear to catch food from far away, we are capable of creating awesome machines to keep ourselves safe. Starting with the invention of the catapult and trebuchet in the 5th century, where very large rocks were projected into the air. By the 9th century, the Chinese had invented gunpowder. These projectiles became even more efficient and accurate in aim through a process of trial and error rather than mathematical calculations.
Our fascination with space and astronomical calculation dates back to ancient times, with contribution from ancient civilizations like India, Greece, Persia, to finally what we now know as Copernicus' heliocentric model of planetary movement. Progress in the field of astronomy and space fueled the development of the mathematics behind projectile motions, which only started to be formally developed in the 14th century at Merton College at the University of Oxford.
Building on the theory of infinitesimal calculus proposed by the ancient Greeks, Chinese, and Indian mathematicians, Sir Isaac Newton in England and Gottfried Leibniz in Germany almost simultaneously developed calculus as we know it today. This led to further improvements in the mathematics necessary to understand projectiles. With the power of calculus, the equations of motion could be developed and the motion of projectiles could be further explained to include orbit of planets. The improvement of materials and the development of more sophisticated mathematics paved the way for us to be able to send the first humans to the moon.
At the same time, humans invented very powerful things during the wartime. We are able to use all those inventions for peaceful means as well. One of my favorite examples of how projectiles can be used for good is satellites.
Planets are examples of projectiles too. So, if we know the science of planetary motion, which Newton was able to give us, we can use it to put anything we want in orbit, such as satellites produced by humans. We just had to wait a few centuries for the technology to catch up. Now, let's listen to the space engineer who helped launch the Bhutan 1 satellite.
Can you tell us about how satellites are launched?
So basically, all the satellites, they are placed inside a rocket and then launched. That's what happened with the Sputnik. It was placed inside a rocket and then the rocket was launched from the Earth's surface. And as the rocket reached space, as it escaped the Earth's gravitational pull, the satellite detached from the rocket and then it started its motion on its own and then started orbiting the Earth. So that is the traditional way of launching a satellite. But in recent days, with advancement of technology, there has been another alternative way of launching a satellite. That is how Bhutan 1 was launched. So like in the conventional way, the satellite is again placed in the rocket, then still the rocket is launched. But now when the rocket reaches space, instead of satellite being detached directly from the rocket and entering the orbit, the rocket first goes to the International Space Station or the ISS. So there the satellite is then taken out from the rocket and then placed inside the ISS. As you might know, we have astronauts living in the ISS throughout the year. So what happens is the astronauts, they manually take the satellite, they place it in what they call as the orbital deployer. So they place the satellite inside of the deployer and then from the ISS, they manually deploy the satellite into the orbit.
I think our viewers will be really interested in knowing how satellites maintain their orbit. So if you could share something on that.
Yeah, so for this question, I will take an example of Bhutan 1. As I mentioned earlier, Bhutan 1 was deployed into the orbit from ISS, International Space Station. So the satellite was placed inside that orbital deployer and then it was deployed from the ISS. So when that happened, the velocity at which the ISS is moving, the satellite gains the same momentum and it starts moving at that same velocity. Now, the satellite does not get enough velocity to go out of or go into the deep space, and as the satellite is deployed, the Earth's gravitational pull starts acting on it. But the pull is not strong enough to bring it down on the Earth's surface. So what happens is the satellite starts moving at the same velocity as that of ISS and then it remains in a free fall. That way satellite keeps revolving around the Earth every day. In a day it makes around 14 to 15 orbit. So that's how satellite continuously remains in orbit.
Can we say that the launch of a satellite is an example of projectile motion?
Yes, in a way it is, but as I was mentioning earlier, the satellite is placed in a rocket and the rocket is launched. The launch of the rocket itself is not a projectile motion. But when the satellite is detached from the rocket, or in the case of ISS launch, as the satellite is released from the ISS, then it gets that initial momentum and then it keeps moving at that same velocity. So from the moment it is detached from the rocket or released from the ISS, it becomes a projectile motion.
Now, let's understand what is a projectile and the forces that influence it as it moves through air. Before we do that, let's explore some more on what qualifies an object to be a projectile. Just because an object or something flies through the air does not make it a projectile. If that were the case, then all flying objects would be called projectiles, including birds. In the case of birds, because they are flapping their wings, they are introducing another force other than gravity. However, if a bird stops flapping its wings and folds them in as it floats in the air, it would be considered as a projectile. So, just to be clear, the scientific definition of projectile motion is the motion experienced when a massive object is projected or dropped and it continues to move by its own inertia and is influenced only by one force, the force of gravity.
You must be wondering if missiles and torpedoes are also classified as projectiles.
They are actually not, because they are constantly being propelled forward, meaning that another force other than gravity is acting on it at all times. For example, torpedoes are being pushed up by buoyancy in water.
As we all know, the force of gravity acts to pull anything towards the center of the earth. And while no one knows what causes the force of gravity, we are very aware of what it causes.
Other forces such as air resistance are often neglected in projectile mathematics, as the projected objects are nowadays very aerodynamical. Aerodynamics means an object that can move through the air with very little drag.
We see aerodynamical shapes all the time in nature, such as river rocks. But it can take millions of years for nature to make something aerodynamic. River rocks were not always aerodynamical. At one point, rocks blocked the passage of the water. You can say that it opposed the motion of the water. Water still finds a way to move around the rock so that it could pass by much more easily. Water flowing around the rock continuously shaped that rock to a point that it offered very little resistance to the water flow. You can say that the water flowing around the rock is the same thing as a crew flowing through the air.
The things we build today that require them moving through the air, such as cars and aeroplanes, are built in such a way that air resistance is as small as possible. This helps save energy in the form of fuel, which is becoming more and more scarce in the world.
Putting our ability to throw things and the principle of aerodynamics together has enabled us humans to achieve some fantastic things. All this was possible because our ancestors observed projectiles that occur in nature, as mentioned earlier, and used their ingenuity to replicate it using observation and mathematics, thus giving birth to the science of projectiles.
I hope you enjoyed learning about the historical developments in the science of projectiles, the example of Bhutan 1 satellite as a practical application of projectile motion, and the different forces that influence projectile motion in this episode.
In the next episode, we will tell you more about the motion of projectile. See you next time. Tashi dile.